Now let's do the following example to build up more experience. So let's use Stoke's theorem to evaluate the line integral of the vector field f over the curve C dr dot dr if the vector field f is angle bracket y comma negative x comma 0 and C is the boundary of the surface S is equal to the following set of points. So the surface is described as points x comma y comma 0 in three-dimensional space, satisfying x squared plus y squared is less than or equal to 9. And this C here is traversed counterclockwise when viewed from above. So let's think about what the picture of the surface is. So this is decidedly points where the z coordinate is 0, meaning the points are all the points of the surface are situated in the xy plane. Even though there's an object in three-dimensional space, the z coordinate's always 0, and then this x squared plus y squared less than or equal to 9, well, isn't that then just all the points that are a distance of at most 3 away from the origin but live in the xy plane? Yeah. So just a picture of that, of the surface. So, okay, x, y, z. So there's this filled in circle, a disk as it's called, so it's a flat object in three-dimensional space, but it's really a two-dimensional object in nature. Now, so that's the surface S, the filled in object. The thing we were asked to do is actually, let's see, there's the curve C. I'm trying to do this in a new color here. C then is around, yeah. So C is that, where S is the filled in disk itself. And if we're looking at C counterclockwise when viewed from above, I've already drawn in orientation arrows for this. I'll do this in red again. Then the orientation of the surface would need to be upwards, right? That's how that upward arrow will correspond to circular arrows that look like this. Okay, but instead of computing the integral directly, right? Instead of computing the line integral, if we're asked to use Stoke's theorem, that means we should think of evaluating the double integral over the surface of the curl of the vector field dotted with n ds. Well, the curl of f, you'll have to work this out. Okay, set up your cross product. You'll end up with 0, 0, negative 2. And then a parameterization of the surface S. And there are lots of choices, but the one I'd like to go with right now is r of u comma v is equal to angle bracket u cosine v, u sine v, comma 0. So this one's inspired by polar coordinates. The parameter domain, d, is, well, u should go between 0 and 3, and v should go between 0 and 2 pi. The normal vector, that is the orientation vector or orientation function for the surface. Well, if we're orienting the surface here upwards, then just everywhere you go, the n vector is just going to be 0, 0, 1. So normally your n vector is actually an n function and can depend on x, y, and z. Here, just due to the fact that the surface is completely flat and it is horizontal, the surface itself is horizontal, we can just use 0, 0, 1. We can also compute instead of noticing it from the picture, if you want, you could just take the parameterization written as a vector function, and you could compute r sub u cross r sub v, do this over the magnitude of that cross product and then look whether you need the plus or the minus signs. You could do it the more long-winded way. We just won't do that right here. In any case, we are going to need to compute r sub u cross r sub v, mainly in the interest of needing to write out what ds is in just a moment. So let's first, okay, if we compute that, we didn't do the partial derivatives here, but if you do, you'll have 0, 0, u, and then that means that computing ds should be, well, the magnitude of the vector we just looked at, so the magnitude of the 0, 0, u vector, times a du dv or a dv du. And so if we go ahead and compute this magnitude, it will end up being u du dv. Yeah, vector 0, 0, u is just going to have magnitude u as long as u is positive, which is what we have in this example. Okay, it's, I hope, kind of fairly just reminiscent to us that this really looks like an r dr d theta. It's just really a comment about what setting up integrals in polar coordinates looked like a long time ago. Okay, so then instead of computing the integral, scrolling up just a moment, instead of computing the line integral directly, so the line integral itself, the line integral of the vector field, is instead, due to Stoke's theorem, going to be computed as the integral over the surface of the curl of the vector field dotted with the orientation vector function for the surface ds, and we've now computed many pieces of this, so let's just draw those integral signs, give a little bit of room for this. We've got the curl of f, which was 0, 0, negative 2, dotted with the normal vector, this n vector up here, which was 0, 0, 1, and then we need ds, so we need u times du times dv, so u du dv. This is telling us now that since u is on the inside, the u integral goes from 0 to 3 and the v integral from 0 to 2 pi. This dot product is actually not bad, so let's go ahead and actually compute this in full. We've got negative 2 u du dv, and if you work through some details here, you're going to end up with negative 18 pi. Now that number negative 18 pi, I hope actually looks familiar because of the following thing. So last time, we actually had a surface, let's say a different surface. So I'm going to call it S sub 2. So look back to what we did last time. I hope you have notes for it. But last time we had a surface which was described this way: x squared plus y squared plus z squared equals 9 and z greater than or equal to 0. So that was the top half of, that was a hemisphere, the northern hemisphere, right? That's a different surface than the one we had here. This surface that we just looked at was flat. Though it turned out that the boundary of this surface we looked at last time was x squared plus y squared equals 9 and z equals 0. It was actually the same circle that we had noticed over here. That's drawn in red. The vector field that we had in a problem in this problem last time was, well, same vector field, y negative x 0. And I'd like to remind you, it was our first example that we did last time to help verify. Now, we didn't prove Stoke's theorem, but just to at least see what was going on, see that two computations gave us the same number. And what we had computed was that the line integral of this vector field over the curve C was negative 18 pi. Okay, and this was done by parametrizing C. Go back and look that's we actually did that. And then the surface integral over this new surface, it was the surface from last time, of curl of f dot ds, or if we write it as double integral over the surface of curl of f dotted with a different n vector, okay, ds. We also got this to be negative 18 pi, and we did this by parametrizing s sub 2, I guess here, yeah, by parametrizing the the northern hemisphere. But here's the thing I want you to notice is that we got negative 18 pi here and there. And last time we just wanted to show we had the same the same number for two different problems just to have a verification of sort of a live example of what's going on with Stokes' theorem. But take a look. We have a negative 18 pi here again. Wait a second. What's going on? The important thing to say here is the following. We're going to build now ourselves a new technique, a very advanced technique. If S1 and S2 are oriented surfaces, so you have two different surfaces, S1 and S2, but these two surfaces have the same, with the same, let's say oriented for clarity here, with the same oriented boundary, capital C, that is, the boundary of surface 1 is equal to C, which is also equal to the boundary of S2. Okay, then check out this really neat thing that occurs. This is really, how do you say this? This is really profound. Okay, so the integral over the surface of the curl of vector field F dot n, say n sub 1 as the orientation for the surface 1. Okay, this is equal to, using Stokes' theorem, the line integral over the curve C of the vector field F dot dr, which is equal to, by Stokes' theorem, the integral over the surface, now surface number 2, S2, of curl of the vector field dot orientation of the second surface, so n sub 2 ds. So what's going on is going from here to here is using Stokes' theorem in one direction, and then going from here to there is using Stokes' theorem in another direction. But why would you ever do this? Well, you can run into situations where this part here might be challenging, difficult, or maybe it could be done, but it'd be annoying, and then maybe this problem here might be easy. So think about it. In what we were dealing with here, I'd say that the difficult integral is represented by the one yesterday, where we had to parameterize the top half of the surface of a sphere. Now, it's not the worst thing in the world, but if you had your pick between the top half of the surface of a sphere or integrating, well, still curl of the same vector field, but the surface is now completely flat, right? The surface here was this nice flat coin right there. Then, strategically, we just make a nice choice to say, instead of doing the difficult problem, we'll do this easy problem instead, and we won't even really do the problem in the middle.